Thank you, Mr. Chairman, for your introduction. As you said, my name is Danilo D'Angelo. I am from the University of Greenwich in London, and the paper is entitled Acoustic Emission Entropy as a fracture-sensitive feature for real-time assessment of metal components under fatigue loading. The presentation is structured into 5 parts. In the first one, I'll introduce the contents. The second, I'll show the experimental testing is performed. In the third, the acoustic emission data analysis. In the fourth, I'll show the results. And in the fifth, I'll discuss and I'll trace the conclusions. We will start from the contents that is actually the application of this study, the aim application to bridges. We all know how bridges are highly vulnerable and exposed to damage, and how important is the single components of bridge. In fact, the degradation of one or few bridge components is likely to cause global performance deficiency. Metallic bridges are among the most sensitive structures. In fact, in the last years, the most collapsed bridges were metallic bridges, and the combination of fatigue fracture used to be the most probable cause of failure. Acoustic emission testing is an innovative, passive, non-destructive monitoring technique that is often used for the evaluation and assessment of the safety of bridges. It is widely used, but is still challenging essentially due to the complexity and the randomness of the acoustic phenomena, the noise disturbance due to, for example, traffic loads, and the timeless continuous monitoring that is often typical of real monitoring of structures. The figure you can see the typical application of acoustic emission testing, and below, just to stress the complexity and the chaotic behavior of acoustic waves, I just wanted to show how hard is the interpretation of data according to traditional approaches. The aims of the study actually is one big aim to improve the application of the technique for real-time periodic monitoring of metal fracture critical bridge components within an extremely noisy environment. The methodology is based on the acoustic emission testing of fracture crack growth in compactentious specimens, and actually through the evaluation real-time of the information entropy of the acoustic emission data using both the Shannon and the Kullback library formulations over timeless continuous windows of monitoring processes. We carried out experimental tests on 4 compactentious specimens, fatigue crack growth testing, and we used one single channel USB system produced by Mistras Limited. And we used one ultra-low noise preamplified sensor, resonant at 300 kHz. The particular application was actually that the sensor was not on the sample, like it is usually done, but was on the fatigue machine, in order to take into account the cyclic noise, I would say, due to the equipment, the mechanical equipment. You can see the geometry of the sample. We tested 4 samples. 2 were aluminum, 7075D6, and 2 were steel 355. For the acoustic emission data analysis, we firstly filtered the data using the Swanson filtering technique and using the limits for amplitude and duration suggested in the literature, that you can see the figure. Preliminarily, we performed the traditional acoustic emission analysis by historical comparison and correlation analysis, and then we evaluated the information entropy of the acoustic emission data using both the formulations, the classical Shannon entropy information, using information and statistical mechanics that you can see on the left, HS in this case, and the relative measure of entropy using the Kullback library formulation, as you can see. Actually, the evaluation is based on the counts, so as you can see, NK is the number of A counts, CI is the cumulative number of counts. According to the number of counts, we can calculate the vector of the probability that is defined in the equation, and using the definition of PI, we can calculate both different measures of entropy. Let's have a look at the results. This is actually the historical plots. It is the basic way to assess, to evaluate the acoustic data. We see the 4 cases analyzed. A1 and 2 are related to the aluminum samples, S1 and S2 are related to the steel samples. We can see the dashed line, actually, the dashed line, the first one is related to the crack initiation that was experimentally assessed during the testing. As you can see also, there is the thicker dashed line that is related to the failure occurring. It's clear that this very simple assessment of the acoustic data is not able to detect both crack initiation and of course, failure, but with failure, actually, as you see, we can detect it just prior to the occurring of the failure. We are not able to detect this in advance. So, and also we see that the activity, the entity of the activity is extremely varied due to the different testing and sample conditions. We also apply the behavior analysis, even if it's not very common for this specific application. Okay, this comes from the very famous magnitude-frequency relation from Mudermeyer-Richter, from earthquake seismology. And you can see the four results, the 4 case results. And only in the case of the aluminum samples, we saw actually a decreasing of the p-value as long as the damage increased. In the other 2 cases, this was not observed. Therefore, we can say that this method was not valid for this specific application. Finally, let's go to the acoustic entropy evaluation. You can see the 4 cases analyzed. We see on the left axis the Shannon entropy, on the right axis the relative measure of entropy. We see that in this case, despite the different testing and sample conditions, we have a very similar trend, a pattern, that is also, we will see in a while, correlated to the damage occurring. So actually, with regard to the Shannon entropy, we identified 4 stages. The first one, there is a short duration subvertical tangent branch, as you can see here. After we have a smooth knee, stage 3 is defined by decreasing tangent branch, and the 4th and last is a long duration subhorizontal tangent branch that we also can define as a plateau. A similar pattern was identified with regard to relative entropy. Actually, we have a short duration subvertical tangent branch, a less smooth abrupt knee, a long duration subhorizontal tangent branch, plateau, but actually, in 1 case out of 4, there is an irregular increasing branch just prior to the failure, in the case A2, as you can see on the top right. Actually, according to this trend, we established some damage correlations. In case of Shannon entropy, the crack initiation was associated with the transition between the stages 2 and 3, while the crack propagation was related to the stage 3. The failure was related to stage 4. For the relative entropy, actually the crack initiation is related to the onset of the stage 3, the crack propagation to the whole stage 3, and the failure, differently from the other cases, is related to a threshold value of the entropy. We can see how these damage correlations work more effectively than the historical plots and the correlation analysis we showed. This can be easily implemented on structural health monitoring. Actually, before that, since I said we wanted to focus on the periodic monitoring, okay, here we see time continuous results. So the acoustic waves are monitored from the beginning of the test until the failure. So the step, the following step actually was the evaluation in time discontinuous windows of testing. Actually, before showing the result, I need to define the random monitoring process. It is a randomly selected time-ordered detection window. So we have a certain number of discrete detection windows over which we evaluated the entropy in order to see if this approach is suitable for real monitoring that actually is rarely time continuous. The detection windows are defined, as I said, like time intervals during which the acoustic data are recorded and the entropy is assessed. On the right, you can see actually 5 main results. The solid line is related to the time continuous evaluation of the Shannon entropy. The other cases are related to these random monitoring processes. And what is varied here is the number of detection windows, NDW. Okay, we found that even if we vary the number of detection windows, okay, ranging from the 5% of the whole lifetime evaluated up to the 50%, the trend doesn't change. This means that even if we monitor just the 5% of the whole testing, in this case, we are able to define the trend as well. This approach was preliminarily applied in order to define a monitoring protocol to be applied to real structural monitoring of bridges. Actually, we evaluated, according to this method, this approach, we developed this protocol, and it is based actually on the real-time evaluation of the entropy, the Shannon entropy of these time discontinuous detection windows. The protocol is based on the comparison, the ongoing, real-time comparison of the current acoustic emission entropy with previous values of entropy according to two experimentally established criteria that are based actually on the correlations we can see here. So the assessment of this comparison allows us to define in real time the timing criteria and the alarm criteria. The time criteria define the following inspection. When is the following inspection due? This is actually a function of the current response of the comparison between the current entropy and the previous evaluated entropies. This also allows to define the alarm cases with the consequent actions to be undertaken. As a preliminary result, I only show here a curve to show the potential, the promising approach. You can see here, dashed line is the global curve, time continuous. The black one, as you see, is a step diagram that actually is evaluated according to the protocol. So the vertical line, actually, the sub-vertical line are the only evaluated windows of the acoustic emission testing. We assume a constant cumulative acoustic entropy in between the different detection windows. As you can see, this approach allows to actually detect the fracture initiation just after this occurs, as well as to predict the failure, in this case about the 60% of the lifetime, because of course failure happens at normalized time equal to 1. This is just to show you that this approach could be applied. So we found that the traditional analysis did not allow to define unequivocal damage correlations. Maybe this is due to the noise condition. Let's not forget that the sensor is on the equipment, and we detected this very significant cyclic noise. The crack initiation, the fractal propagation, and the failure were well correlated, on the contrary, to both the entropy evaluation, also with regard to time discontinuous evaluation, and this actually represents a proof that this approach could be potentially applied to the structural echo monitoring. Of course, we need to carry out further studies in order to check the robustness of this approach. Okay, here you can find the references. Thank you so much for your attention.